It's a wonderful pleasure to introduce David Mumford. He has a list of honors and recognitions that's longer than anybody's arm. I won't quote those, aside from the fact that he was a Fields medalist, of course, for his work in algebraic geometry, and then went on to have another entire second career in applied mathematics. And I'll just say a couple of things that are pertinent to this organization. Of course, he was also the president of IMU. But the most important thing for Fields, the Fields Institute, is that David was one of the first members of the scientific advisory panel. Jerry Marsden and I sat down to make a dream team list of people to put on that panel to really put us on the map intellectually. And every one of them accepted. Thank you, David. And by the way, it was Carl Ream who made the invitation to David, because we divided the list up among the people we knew best each. And neither of us knew David all that well, but Carl and Elaine Ream knew him. And Carl was the one that persuaded David to get on that ship. And thank goodness he did.
That's true. And it was a pleasure.
Well,
it was a great pleasure.
So the topic is, how will AI affect mathematical research? I have my ideas about that, so I have at least one question for you, and I imagine many other people do, but without further ado, David, please, let's start.
Very good. I just can't resist making a comment about Gromov's talk. It's, he had that slide which showed the complexity of the transfer RNA, and how, I've looked at it and looked at the details a little bit, and it all seems like a really random combination of many possibilities. And in any case, it's looking at that convinced me to believe in what people call panspermia. The idea that the Earth was seeded by some single-celled life that has been broadcast by heaven knows whom in all directions. Anyway, so I I should say my personal involvement with AI was through several decades studying computer vision, because it looked to me and looked to all the researchers at that point that general AI was much too difficult, and it was good to concentrate on a smaller subset. But then around 1910, in 2010, I should say, everything changed with deep learning. But so let me begin. Oh, wait a minute now. Oh, why is it? Oh, I do it this way. Okay. So what is the problem if you try to prove theorems with a computer? Well, they come in two sorts. The first problem is that the satisfiability of a random Boolean expression is NP complete, which means given that a certain miracle doesn't take place, that really you simply have to check the possible values of the Boolean variables one at a time. So it takes, if it has n variables, you have 2 to the n possibilities. So that's the first big obstacles. The second one comes about because predicate calculus is also problematic. What you can do is, it is a Gödel's theorem that any propositional statement with some set of axioms, which is true in all models, can be proven. by Skolemization, for example. But the length of the fastest proof grows so incredibly fast that that you cannot even define it within piano arithmetic. It's comparable to the rate of growth of some of these crazy Ramsey combinatorial statements. Okay, so in other words, brute force is not going to get us anywhere. Okay, so I think the state of the art is that people have been studying very restricted fields, Euclidean geometry, formulas for integrals and special functions, Grosvenor bases, and algebraic geometry, which have been, which are useful, but they're very limited. And there's also a school of thought, the univalent foundations people, who believe that that their radical reformulation, which discards set theory and instead replaces it with types in a hierarchy of winding up with infinity categories. And it's utterly weird because it really unites the ontology and the epistemology, that is to say, the objects we're thinking about and what we know about them are all in an extraordinary way thrown into the same basket. Okay, and it has had some successes in the sense that they verified the classification of finite simple groups. Anyway, that's but I think it's worthwhile to look at the roots of mathematics, because mathematics did not spring up as somebody sitting down and saying, I think I'll define a group this way, a set with a certain law of compositions, etc. No, it started in very concrete problems. So city-states needed to have serious accounts, which and this was developed in Mesopotamia, really in the 3rd century before the Common Era, and along with this sexagesimal notation. Anyway, but they also needed to tax land, so geometry was invented. I mean, the word geometry is measuring the earth. And then, so these are the roots of algebra and geometry, but then the roots of analysis came from these simple machines, which, even in Stonehenge, they seem to have been able to move these incredible rocks 100 miles or something. And it seems to me, looking at the history, that until 1950, pure and applied mathematics were one. This is a lovely diagram, which I stumbled on via Google, of course. College mathematics as it was taught in 1772. And you can see down there in the bottom, there's fluxions and logarithms. Then there's bookkeeping and what is this one? Navigation, surveying, astronomy. So there is a total blend, in other words, of pure mathematics and applied math. So what I want to argue for in this talk is that we need to look a little more closely at how human beings are actually, what's going on in their heads when they do math. So, okay, so deep learning totally transformed the lay of the land. So these large language models came about when huge databases were available, and people realized that they could use the graphical processing unit. Now they have specialized chips precisely for doing AI, because the algorithms of AI are mostly incredibly simple, and therefore, what you really need is a chip which can do parallel computations on a massive scale. Okay, so, but I want to emphasize that there's two things that, to me, are above and beyond simply the success of the algorithms of deep learning, which go back to the 40s. One of them is the whole idea of representing a word by a truly huge vector of real numbers, like 10 to the 1024. And the other thing which Google invented was what they called the transformer, which is essentially a way of taking linear projections and having a much lower dimensional representation for a specific information which connects one thing with another. It establishes context. So, right. So how did the large language models work? Well, first they're trained to simply predict a missing word in a sentence. And then as they get more totally successful in that, they're trained to produce a second sentence, which is a continuation of the first. And as I'm sure you've all played with it, it's incredible, but it has limits. So it does not know. No one has told it that Santa Claus does not exist. As far as I know, it simply doesn't know the difference between novels and myths and the real world. So it hallucinates things all the time. So actually, I gave a similar talk at Boston University. So that's preparing this talk was that. There was a logic problem called Schubert's steamroller. I don't know why. About wolves, foxes, birds, caterpillars, and snails, and who eats what. So there are these. I mean, basically, it's a logic problem, and and believe it or not, I don't know. It's Open GPT. I don't know which of the GPTs it was, but it got it wrong. Actually, I've kind of forgotten what I think it's foxes or something, but anyway, it got it wrong. It's really not good at logic. But a marvelous, I mean, people keep working really hard by isolating a specific problem. And the point is that the Math Olympiad, one component, are really killer problems in Euclidean geometry. So if you look at the diagram here, you start with an arbitrary triangle ABC. It has an orthocenter H, whose foot is on BG is called F. And then you take the midpoint of BG, and then you take the semicircle. Yeah, well, you can read it. Anyway, it's quite elaborate. And then you have to prove that the circumcircles of FKM and KQH are tangent at K. Well, good luck. I wouldn't attempt to do it myself. Now, why is that? But so when you have these killer problems, what is the essential step? What it is that you have to introduce some new points. In this case, the points D, G, and E are introduced in order to carry out the proof. So basically, the computer is very good. If you have a fixed set of points, and therefore line segments and circles, it can really make an exhaustive list of every consequence, what is congruent to what, and so on, what angles are equal. That's a sort of mechanical thing, but it's the idea of suggesting a new point and introducing that in order to solve the problem. So what these guys at Google did, their team, they call it alpha geometry. They combined, first of all, the mechanical part, which the computer was really good at. And then they began to use deep learning to guess the auxiliary points. So, you know, deep learning is basically trained to find patterns of some kind from many, many examples. So they give it, I don't know how many tricky Euclidean geometry problems they had, but but they gave those a mess of them and trained. So in this case, it guessed that these 3 points D, G, and E were needed. And overall, there's an article in Nature that I referred to there. It's not 100%. It does not get them all, but it reaches the gold medal level, whatever that is, in the Olympiad. So I think this is a really important example because it shows that one method may not by itself be the answer. Here's another example from Google. There was a traditional problem in AI called Block's World, which was an early example of doing Mickey Mouse things with blocks, but now they have a smart robot that can move around and has a gripper, and you ask it, bring me the rice chips from the drawer. And not only that, but you can see adversarial disturbance. You make it harder because you knock the thing out of its grip, but it recovers. Anyway, it does it. And this, I sort of feel that this is still on a very crude level, but it is the beginning of really integrating deep learning with real life and robots. And I feel fairly certain that really smart robots will be built. I mean, there's so many companies working on it. I mean, startups. I mean, it used to be that in computer science, they were really marvelous at using the archive, and every lab published all its results in the archive. No longer. Now it's competition. So you don't really know what people are doing. So, so I want to suggest that it's very similar to a baby learning. It's lying on its back in the crib and it reaches its hand up and there's a rattle or something and it learns that it can hit the rattle and make it rattle. So hand-eye coordination is one of the first skills. But the robot has to, of course, go way beyond that and learn, for instance, about solids, liquids, and gas. That was the sort of thing that people felt was going to be really tricky. But I think if the robot is actually doing these things, it's going to be much easier because it will generate its own feedback instead of relying on canned texts. Right. So yeah, so it learns what a line is, that that a line is a straight thing and a circle is a round thing. I mean, I don't think alpha geometry had a clue what the diagram that we use was all about. So I think that it's really going to get around the problem of hallucinations and be able to understand that you have to interpret logic carefully with everything being checked, or else you're going to make errors. So I think this will come naturally once you have robots. But the interesting question is the architecture. I mean, so far, the large language models, basically, they have a whole set of layers on the input, which translates the sentence into an incomprehensible string of real numbers. I mean, I don't know, tens of thousands. And then it has a synthesis part in which it then answers the question which has been posed and produces now an English sentence or whatever language you ask it to do. Now, the brain is not like that. All mammal brains, and it would appear, although the research is not so advanced, bird brains, are divided into these areas. So the picture here is the large proportion of a mouse cortex flattened, so you can make a diagram, and the different areas are labeled. So SS stands for somatosensory. Aud is obviously hearing. Viz is vision. MO is motion. The memory part is they couldn't flatten it simultaneously with everything else. So, but now the point is that what's happening? I'm getting my partner is playing some music. Anyway, how do they identify these areas? It's because within each area there are rich interconnections, but between areas you go through the white matter and you have a separate one-way passages, one being apparently feed forward as the calculation proceeds, and the other being feedback. So so you identify these, and here's a picture of what is it? Some sort of monkey. and with the various areas in the monkey colored, vividly colored. And it also turns out that there are very distinctly lower areas and higher areas. So that's what feed forward means. That those are paths from the lower to the higher. And you see, I believe that this whole architecture is going to have to be adopted once you really begin to integrate language, motion, hearing, and vision in a robot. I mean, you're going to need a more complicated architecture. And I see this whole thing as really being a form of Bayesian optimization. The feedback pathways use the memories of what you've seen before and see if it matches what the new data is. And if it doesn't match, it alters synaptic weights. So it's really following a version of Bayes' rule to do the calculation. So that's a conjecture anyway. How am I doing time-wise? Oh, I'm doing okay. I don't think I'm going to talk. Okay, so now people are all arguing about how dangerous AI is going to be. And I just want to point out a few things. I do believe that we are going to have fully functional robots. Well, I might say a decade or two. And I think they're going to have to develop a more complicated architecture, similar to mammals. So, yeah, will they be able to do math? Well, I think they can take a course. They can learn math just the way humans do. Once they understand the basics and they understand English and they understand logic, they can take a math course and study, listen to lectures and absorb all the information. And they will have a very clear idea what is the real world and what is the fantasy world that many politicians live in. So, I mean, and they'll have agency. They can do things. They can make up their mind and decide to do something. I think the real issue is going to come when some people get fond of their robots. There have been novels written about this, of course. And I think there are going to be huge debates over whether or not these robots are conscious, whether they have awareness and feel the same sense of living that we do. I don't think there'll be any. They're going to be endless debates. But the important thing is, the Sorcerer's Apprentice is what people always talk about. I thought that was invented by Disney, but it actually was written by Goethe. And I mean, believe it or not, around 1800, they already worried about mechanical machines taking over from human beings. So the Sorcerer's Apprentice gets out of hand. But the key point is that, for heaven's sake, we programmers program in the drives, the fundamental drives that what does the large language model want to optimize? well, it's optimized to imitate human discourse. Uh, and then it has some boundaries. So it's been purposefully instructed not to reproduce porn, for instance, or hate speech. So unless it's programmed, I don't think it's going to worry about death. There's actually, my favorite book is Ian McEwan's book, Machines Like Me, where this robot does resist being turned off. And in fact, it gets out of hand because, why does it get out of hand, by the way? It's because human emotions are so tricky to understand. And he misses the deep levels of the way people are interacting with what emotions are present. So the question which is continually raised is, if the computer does math, is it going to, does it know what beautiful math is and ugly math? I mean, so I would certainly say that geometry problem that it solved was an ugly Euclidean problem. There was nothing elegant about it or particularly illuminating. And you know, maybe human creativity has a lot to do with dreaming, because when you dream, random combinations of thoughts really come into your head, and it's making connections in ways that startling ways that you didn't do at first. So anyway, it's my conclusion that I think these machines will work the best if they work with a human collaborator. I can easily imagine that within a decade, there's going to be a lot of problems where the computer is enlisted to do the more mechanical side, and also to make suggestions from its, I mean, what is it? It's certainly intuition is what deep learning is all about. I mean, it's putting together ideas in these huge vectors, and it's mixing them up all the time. So I mean, it's really, I mean, what they call fully connected layers takes every unit in layer one and projects the linear signal to the next layer up. So yeah, I mean, I don't really see why a certain amount of imagination really should be a natural sort of link with robots. Yeah, wait a minute. But you know, when I began to think about this, you know, being an octogenarian, you have this, you have a different perspective. I mean, you've come from when you were a student. It's almost nobody had heard about cohomology, but now I think every pure mathematician knows a certain amount about cohomology. I mean, it was the new wave. So, and what strikes me, looking back at my own lifetime of experience, is that some areas seem to get weaker because too much is solved. I mean, it's startling that with Kolar's work and Mori's work, higher dimensional algebraic varieties have been largely tamed. I mean, okay, they haven't proved every theorem in a final form, but they have such strong tools now, and so much has been proven that I sort of see algebraic geometry as being a totally different field. I mean, the big exception is there's been zero progress on the Hodge conjecture. In general, higher codimension subvarieties are a mess. No one really understands them at all. But then there's areas which, so I got into this a little bit when I got involved with computer vision. I got very intrigued with these infinite dimensional Riemannian manifolds that are made up of, for instance, simple closed plane curves. There are many different metrics you can put on the, and it's an infinite dimensional space, perfectly. Of course, there's always the degree of complexity of the curve, how zigzaggy it is, but yeah. But anyway, it's I sort of see nonlinear PDEs as being a wild west, and I would think that computers have may be able to contribute a lot. And how about I mean, areas where there's so much calculation going on, like Langland's conjectures. But I don't know, P equals NP is that's going to require some utterly different approach. So, and I don't think it's likely that sort of problem, that computers are going to be much help. I would certainly hope that some human is able to prove that P is not equal to NP within the next generation. And likewise, that the zeta zeros are all on imaginary part equals 1/2. But maybe not. And if computers can help, I think one can be more optimistic. Okay, that's my talk.